Hi and welcome. This time I will try to create asynchronous delays to control two LED diodes. This type of delay is suitable for multitasking processes and cooperative processing. A timer greater than 16 bits is needed, ideally a 32-bit timer. According to the ATF32 datasheets, timers 2 or 5 can be extended to the necessary width. There is also the central timer, called SysTick, which is 24 bits and could be useful. The timer called SysTick, in addition to being 24-bit, is indicated to be a decrement counter with automatic reload of its value upon overflow. It can generate an overflow interrupt and has 2 clock sources. To find an example related to this timer and any other peripheral, I need to go to the Microcontroller's website, and in the section called BSB, we can download the file named firmware library to get examples that are very useful. The path where there is an example with that timer is in the examples folder, and then in the Cortex M4 folder, as shown in this image. The project was generated with the help of a tool called WorkBench, as referenced in the video titled. A quick look at the ATF32 WorkBench tool, which I'll link to in the description. It's essentially the same, with the following differences. Now I'm using 2 pins as outputs to activate the yellow and green LED diodes on the board. In the clock configuration, I've used 2 frequency dividers so that the SysTick timer runs at 7.5 MHz. This could potentially be a disadvantage since other peripherals operate at a lower speed. The reason for reducing the timer frequency is to achieve longer delays, as I'll explain next. I know that for every period of 7.5 MHz, the SysTick decrements by 1 unit. If the timer counts all its 24 bits, we can determine the maximum time that the SysTick could measure. This is achieved through a simple mathematical proportion, and the maximum time is just over 2 seconds. If the frequency were higher than 7.5 MHz, that time would be shorter, which is why I have reduced the frequency. For this project, one LED will blink every 500 milliseconds, while the other will blink every second. For times greater than 2 seconds, we would need to use auxiliary variables to generate longer delays, but this can be cumbersome. That's why a 32-bit timer is much better suited. Again, using a mathematical proportion, to achieve 1 second, the timer should reach a value of 7,500,000 counts, and obviously half of that would be 500 milliseconds. Here's the code. Before the main loop, I've added the SysTick configuration. The load register holds the starting value for countdown, set to its maximum 24-bit value. The VO register counts down and can start from any value, but I've initialized it to 0. In the control register, I've commented out the flag that activates interrupt on overflow because I don't need it. I only activate the timer. I'm using 2 auxiliary variables named delay, 1 for each LED. These variables called delay are defined a bit higher up and are 32-bit unsigned. Now I will explain what happens in the main loop. Basically, there are 2 cooperative tasks for each LED that are independent. Each one is determined by what the if statement does. In the first if statement, what happens is taking the value of the timer at that moment and subtracting it from the delay variable. If the result of this subtraction is greater than the number of cycles equivalent to 500 milliseconds, it can be affirmed that this time has elapsed and the if statement is satisfied. Upon meeting the condition, the state of the terminal assigned to the LED is toggled. Next, the delay variable is updated with the current value of the timer, allowing another asynchronous delay to be generated. The other task is basically the same as the previous one, but it differs in that the delay is 1000 milliseconds, or 1 second, and the blinking is with the yellow LED. The constants 500 milliseconds and 1000 milliseconds are definitions that are higher up, and their values correspond to the ones calculated earlier. Regarding the function that toggles an output terminal on the microcontroller, I couldn't find it within the software's built-in libraries, so I wrote my own function. The parameters required are the port and the pin that need to be toggled. Within the function, it reads the state of the bit, and if it's high, it changes it to low, and vice versa if the bit is low. Something I need to explain is that if the subtraction inside the if statement doesn't work correctly. Although the val register and the delay variable are unsigned, if delay is greater than val, it could be negative. In other compilers, the result is usually the absolute value, so there's no need to worry. So let's test if it works, and if not, I should get the absolute value of that subtraction to make it work correctly. Here is the ATF32 Start F407 board, and I'm connecting the programming and debugging USB cable to my computer. You can see that the project from the previous video, which I have linked in the description, that activates the red LED using the user button, is working correctly. Now I navigate to the project and right-click on it. I click on the option named Debug As, and select Debug Configurations. In the @link option, it is empty, so I right-click on it and choose New Configuration. I check that everything is correct and press the Debug button. The project is recompiled, and ATF32 communicates with the programmer debugger. You can see that the program is about to start executing the first line of the project's code. I press the button to continue running the code without stopping anywhere, and it can be seen that the LED diodes are constantly on, meaning they are not blinking. Another mistake of mine is that I chose the red LED terminal as if it were the green one, but it doesn't matter, that's the least critical. I set a breakpoint where the state of the green diode changes, which is actually the red LED diode, and automatically, the program stops at that line, indicating that the if condition is possibly always being met. I performed some tests navigating through the code, and it can be seen that the program does what it has to do, that is, read the state of the LED diodes and, based on that reading, change their state to high or low. But what doesn't seem to work is the subtraction of the content of the val register with the variables called delay. I could start analyzing whether the result of the subtraction is negative. But I'd rather stop the program and go to the top to place a function that gets the absolute value of the subtraction of two numbers. I could use a built-in compiler function, but I prefer to implement something I have on hand. I place this new function where the if instructions are, in the main loop. I simply comment out the original code so it remains as a record of what was originally attempted. I save the changes made and proceed to recompile the project. There are no compilation errors, so I press the button to debug, and ATF32 tries and succeeds in communicating with the programmer. Then the code stops at the first line, ready for debugging. I press the button to run the program continuously, and the program stops at the breakpoints that were previously set. I disable both breakpoints, and then press the button again to run the code continuously. And now I've done it. You can see how the LED diodes blink. One blinks every 1000 milliseconds, and the other every 500 milliseconds. That's all, thank you for watching the video.